Okay, thanks everyone for coming. So we have a speaker today who doesn't need much introduction many places, but certainly not here. Everyone will know Joel Hamkins, back from Notre Dame, to talk to us about how we might have viewed the continuum hypothesis as a fundamental axiom.
Well, thank you very much for the introduction, and it's such an honor to be here at the PhilMath seminar, and such a pleasure to be back in Oxford and see so many friends. So I want to talk about the continuum hypothesis, so let's just jump right into it. I'm going to go pretty quickly through the kind of background stuff, which I'm hoping is familiar to many people, and then we're going to get into the new part, which is the thought experiment argument in this third section. So let me just jump into it. Okay, Cantor famously proved that the reals are uncountable. The cardinality of the reals is strictly larger than the natural numbers. And so once you do that, of course, it's an extremely natural question to ask if there's any infinity in between them. And he formulated the continuum hypothesis, which is the assertion that there is no infinity in between the natural numbers and the real numbers. And so, in other words, in ZFC, the continuum hypothesis asserts that the continuum is the first uncountable infinity. So, of course, in ZFC, we have all these cardinals here, and we can prove they're the same. The cardinality of the reals, or the continuum. Beth 1 is the same as that 2 to the olive 0, or the power set of the natural numbers. Those are provably equivalent. In ZFC, the new part of the continuum hypothesis is that these cardinals are all also equal to olive 1. Okay, it was formulated in the late 19th century, and he spent his life in frustration trying to prove or refute it without ever coming to an answer. It was the first problem on Hilbert's famous list of open problems that went on to guide 20th century mathematical research. Cantor proved that it holds for closed sets. It's easy to show it holds for open sets. He proved it for closed sets with the Cantor-Bendixson theorem. And that he had the idea of sort of working up to more complicated sets, and that strategy is partially fulfilled because, for example, it follows from the existence of large cardinals that the continuum hypothesis also holds for all projectively definable sets, which is a way of continuing that idea. Okay, it was open for decades until 1938. Kurt Gödel at least proved you cannot refute the continuum hypothesis because he proved that CH holds in the constructible universe L. So this is the set theoretic universe that he constructed, in which all of the ZFC axioms are true, as well as the continuum hypothesis and the generalized continuum hypothesis. So because of this, if ZF is consistent, it follows that ZF plus the axiom of choice plus the continuum hypothesis is also consistent. Okay, then it was several more decades until we had the Cohen result showing that you also cannot prove the continuum hypothesis. And this is using the method of forcing, of course, which allows you to take any model of set theory and construct a larger model of set theory, the forcing extension. And you can do so in such a way that CH fails in the extension. Okay, so therefore the continuum hypothesis is independent of the axioms of ZFC. It's neither provable nor refutable. In fact, the forcing argument shows not just that you can force not CH, but you can also force the positive version CH itself. So if you have any model of set theory, then you can go to a forcing extension where CH is true, and another one where it's false, and a further one where it's true. You can turn it on and off like a light switch. And in fact, CH is an example of a kind of statement that's called a switch in the modal logic of forcing, a statement that you can turn on and off, like an OR sentence, if you know what that means. Okay, by now, forcing has been used in thousands of arguments and has helped to reveal a pervasive ubiquity of the independence phenomenon. Almost every non-trivial assertion of infinite combinatorics has been shown independent of CFC. This is the general situation. CH was maybe the first instance of this. Okay, so none of that really answers the question whether it's true. Maybe this is the question we really want to know. Is it true or not? Of course, the independence might just be showing us that ZFC is a weak theory. Any non-trivial statement is independent over any sufficiently weak theory. So the fact that CH is independent of ZFC might not be significant. It might just be saying, look, we need to strengthen the base theory in order to settle these fundamental questions. Gödel had hoped that we would settle CH by the strong axioms of infinity, by the large cardinals, but this turns out to be wrong in light of the Levi-Solovay theorem, which shows us that all of the large cardinal hypotheses, all of the common ones, so inaccessible cardinals, Mahalo cardinals, weakly compact, measurable, superconvex, everything, all of them are preserved by the forcing both of CH and of not CH. So if you have a large cardinal, then you can have that large cardinal with CH, and you can also have it with not CH, and so there will be none of the large cardinal notions will settle CH in light of this theorem. So the CH is used really throughout set theory. It's true not just in Gödel's constructible universe, but in all of the other canonical inner models that are constructed for large cardinals, so L mu and L E vector and so on. These are the canonical inner models of large cardinals. They all have the continuum hypothesis being true. But also CH is refuted by all of the standard forcing axioms like Martin's axiom at omega 1 or the proper forcing axiom or Martin's maximum. These latter two both imply that the continuum is equal to all of 2. This one doesn't settle it, except it does show that it's at least all of 2. Also, the negation of the continuum hypothesis is routinely considered in the subject of cardinal characteristics of the continuum, where we study the bounding number and the dominating number and the other cardinal characteristics. Because the subject is trivialized under CH, the whole point of that subject is to see how these different cardinal characteristics can differ, but if CH holds, they don't differ. And so it's only interesting in the case of not CH. Okay, so we can't settle CH on the basis of mathematical proof from the ZFC axioms. So set theorists have consequently offered various philosophical arguments in an attempt to settle CH. So I want to mention a few, and then I'm going to get into the new one that this talk is really about. Okay, so one of the most interesting ones to my way of thinking is Freiling's axiom of symmetry. So this is the axiom that says, if you have a function that maps real numbers x to countable sets of real numbers, then there should be 2 real numbers x and y, so that y is not in the set that's attached to x, and x is not in the set that's attached to y. And Freiling gave a kind of philosophical proof of this axiom by thinking about throwing darts at the real line, which is also part of the title of his paper. Okay, so we throw 2 darts at the real line. Maybe the first one lands at some point x, and that point x determines the countable set of real numbers a sub x. So then, almost surely, because it's a countable set, almost surely the second dart is not landing in that set. So it's going to be not in a sub x. And that second point y determines also some countable set a sub y. And now the point of Freiling's argument is that, and the reason why it's called the axiom of symmetry, it shouldn't matter which dart we thought of as the first dart and which dart we thought of as the second dart. There's a kind of symmetry in that choice. And so therefore, we should also think almost surely x is not in the set determined by y. So therefore, neither x nor y is in the other points set. And so we have fulfilled the axiom. And so the argument isn't just that there are these 2 maybe difficult to find points that satisfy that property. The argument is basically almost any 2 points are going to satisfy this property if you just pick them randomly. Okay. So in my experience, it's quite easy to convince a room full of mathematics graduate students of the truth of this axiom using this kind of dart explanation that I've just given. Many mathematicians will readily accept that explanation. Okay, it's a little more difficult if there are senior mathematicians or more experienced people in the room, particularly people who have heard of the axiom before. But if it's the first time, then maybe this argument is a little bit convincing that there should be these 2 points, x and y, that have the property. Okay, so young mathematicians readily agree to this axiom on the basis of Freiling's argument, in my experience. Okay, until you do the second half of the explanation, which is that that axiom, in fact, settles the CH. It's equivalent to the negation of CH. There's an elementary argument showing that the axiom of symmetry is simply equivalent to the negation of CH. So there are some stronger versions. So where you attach not just to one point, but 2 points. Pairs of points are associated with a countable set of real numbers, or maybe you have n tuples of points attached with a countable set of real numbers. And then, for example, in the pair case, then you would throw 3 darts at the real line. And what you're hoping for is that each of the real numbers is not in the set that's determined by the other 2. So that's a kind of slightly stronger version of the axiom of symmetry, which seems to have the same philosophical justification. And it's equivalent to the assertion that the continuum is strictly larger than Olive 2 in the 3 dart case, or Olive n in the n plus 1 dart case. Okay, his theorem was not generally accepted as a solution to CH. It's sort of treated as a kind of curiosity or kind of warning about the non-measurable sets, because in fact, although those sets were countable and so on, we should really be looking at a subset of the plane, the set of pairs x, y, such that x is in the set determined by y. And that set, it doesn't really make sense to talk about sort of almost surely unless you know that that set of pairs is a measurable set, which it generally won't be if the continuum hypothesis holds. And so mathematicians, I mean, who have a kind of more informed attitude about it, reject the Freiling philosophical argument and rather take the result as a warning about the measure theoretic monsters. And that response is somewhat similar to the response that mathematicians give to the Banach-Tarski paradox in regard to the axiom of choice. They accept this bizarre conclusion of the Banach-Tarski paradox. They don't take it as a refutation of AC, but rather as a warning that we need to be careful with non-measurable sets. Okay, Woodin has advanced philosophical arguments actually on both sides of the continuum hypothesis debate. So he made a case years ago for the negation based on considerations of omega logic and forcing absoluteness. But then more recently, he's arguing for CH on the basis of his theory of the ultimate L, which is the canonical inner model accommodating even the largest large cardinals. So Kreisel argues, and also Dan Isaacson defends this view that CH is settled in second order set theory, so second order ZFC. So Zermelo, in his famous quasi-categoricity result, of course, proved that the models of second order ZFC are exactly the models V kappa for inaccessible cardinals kappa. You chop the universe off at an inaccessible. These are also the same thing as the Grothendieck-Zermelo universes that are using category theory. But in particular, they are linearly ordered and they all agree for a long way on initial segments of the universe. And therefore, they will agree on whether CH holds because that's settled already down low at omega plus 2. So all of the models of CFC2 agree on the answer. We don't know which it is. We don't know what the answer is, but they all give the same answer is the point. Okay, critics of this line of reasoning take it as begging the question, it's circular, because the very meaning of second order logic is grounded in set theory. And for example, if you're a pluralist about set theory, then of course you're going to be a pluralist about second order logic. And so different concepts of set are going to give rise to universes in which those V kappas all have the same answer, but they have different answers in the alternative conception. So CH has been really at the center of the debate on pluralism that's taking place in set theory. And on one side of that dichotomy, we have the universe view, also known as set theoretic monism. According to this view, there's a unique absolute background concept of set, which is instantiated in the cumulative universe of all sets. And all set theoretic assertions have a definitive truth value in that set theoretic universe. So every mathematical question comes to its answer. And so in particular, CH has a definite answer according to the universe view. But the main challenge for the universe view, of course, is the central discovery of set theory has been this enormous range of set theoretic possibility. The most powerful tools that we have are most naturally understood as methods of constructing alternative set theoretic universes, alternative set concepts. And I'm thinking of forcing and ultrapowers and all the other methods that we use in set theory to build alternative models of set theory. So set theory has been about constructing as many different models of set theory as possible and made to exhibit diverse features or specific relationships with other models. And so that leads you to the multiverse view, or set theoretic pluralism, which is the philosophical position holding that there are numerous distinct, legitimate concepts of set, each giving rise to its own set theoretic universe. And there's a fruitful analogy to be made with geometry, to my way of thinking. Geometry for thousands of years was viewed as the mathematics of space. There's the one true geometry. But of course, this point of view was splintered with the discovery of non-Euclidean geometry. And now we have many different geometries, hyperbolic space and Euclidean space and so on, spherical geometry, elliptical geometry, and so on. And the point being that basically almost all mathematicians today are pluralists when it comes to geometric truth. And the set theoretic pluralist view is that a similar thing is happening in set theory. Okay. Many set theorists have yearned for what I call a dream solution, by which we settle CH by finding the missing axiom. We're going to find the axiom that we all agree is a manifest principle that's true of the concept of set and which happens to settle CH. But I've argued that this is impossible because of our experience with multiple kinds of set theoretic worlds, some of which have CH and some of which don't. So the situation with CH is not merely that it's formally independent and we don't know anything more about it. Rather, we have an informed, deep understanding of how it could be true and how it could be false. So we grew up in these worlds and we moved from one to the other while controlling other subtle features about them. And therefore, if someone were to present a new principle and prove that it implies not CH, then we couldn't take it as manifestly true. That's exactly what happened with the axiom of symmetry, right? You present this principle, seems manifestly true on the naive account, but then once you know that it implies not CH, then you're no longer really willing to take it as a manifestly true principle. It would be like someone proposing a principle implying that only Brooklyn really exists, but we already know about Manhattan and the other boroughs. Okay. Is CH an open question? Sometimes you can find people in print even saying CH is an open question, but I've argued that it's incorrect to describe CH as an open question. The answer to CH consists of this deep body of knowledge that we have about how it behaves in the set theoretic multiverse, how we can force it or force its negation while controlling for all the other set theoretic features that we might want. That is a kind of answer to CH. Okay, so now I want to move into the new argument that I'm proposing in this talk, a kind of thought experiment. I want to describe how our attitude towards the continuum hypothesis could easily have been very different than it currently is. So I'm going to claim that if our mathematical history had been just a little bit different in a way that I find quite reasonable, if mathematical discoveries had been made in a slightly different order, then we would naturally view the continuum hypothesis as a fundamental axiom, one necessary for mathematics, and indeed indispensable even for calculus. So that's what I want to do. Okay, here's the thought experiment to begin. So let's imagine in the early days of calculus that Newton and Leibniz had provided somewhat fuller accounts of their ideas about infinitesimals. Okay. In the actual world, of course, we didn't have that. It was lacking. I mean, Berkeley famously mocked the foundations of infinitesimals, so writing, and what are these same evanescent increments? They are neither finite quantities nor quantities infinitely small, nor yet nothing. May we not call them the ghosts of departed quantities? Okay, it simply wasn't clear enough what kind of thing the infinitesimals were in the early days. Were they part of the ordinary number system, or did they somehow transcend it? They just weren't clear. So what I want to do is imagine that they were a little bit more clear. I want to imagine that they posited two number realms. The ordinary real numbers And then a larger realm of numbers. I'm going to call them the hyperreal numbers. This is a kind of anachronism to use the contemporary terminology for this thing, but I'm going to use that word anyways. I'm not saying that they would use that word at all. I'm just saying they're positing two number realms, the ordinary numbers, and then this expanded realm that has the infinitesimals in it. And that idea alone immediately addresses, to my way of thinking, the withering Berkeley criticism, because it releases the tension of this paradoxical claim. I mean, the problem with infinitesimals is that they're positive, but they're smaller than every positive number, which just seems contradictory because they would have to be smaller than themselves and so on. But if you have the two number realm idea, it's not a contradiction anymore because you're only saying that the infinitesimals are positive in the larger realm and they're smaller than every positive real number. Okay, so they're fitting in the infinitesimal gap, just like we understand infinitesimals to be. And so there's no contradiction there. It releases that tension, and also it enables us to clarify exactly how the infinitesimal number system relates to the real numbers by having these two number realms. So I think it enables a kind of frank discussion of the nature of real numbers and the infinitesimals and how they work. Okay, so I want to imagine a little bit further. Let's imagine Leibniz clarifying the existence assertions about infinitesimals. Maybe he said something like, every conceivable gap in the real numbers is filled by infinitesimals. So this is the existence assertions for infinitesimals. For example, the gap between the real number 0 and the positive real numbers should have infinitesimals in it, but also there should be hyperreal numbers at infinitesimal distance to the square root of 2 and pi. So on every real number should have its infinitesimal neighborhood. Those are gaps that should be filled according to Leibniz, imaginary Leibniz. Okay, also there's the gap that's above all the real numbers, the infinite hyperreal numbers, and those would be the reciprocals of the infinitesimal numbers near 0. So we would want that the hyperreal field is not Archimedean because of that. So the contemporary perspective on that way of thinking would be that it's an incipient form of saturation, right? Saturation is the principle, countable saturation, says that if you have a weakly increasing sequence of numbers in R star and a weakly decreasing sequence of numbers above it, strictly above it, then there's some hyperreal number strictly in between. Yeah, this is exactly, so we have these two sequences like this, then there should be a hyperreal number strictly in between. This is exactly what it means to be countably saturated. So the reals are not countably saturated. It's something like a Dedekind cut, except it's not a Dedekind cut because we're not saying that Z is the least upper bound. Maybe all the X's are equal to each other, for example. So this is why you're getting infinitesimals that are strictly bigger than a real number, but strictly smaller than the real numbers that are above that real number. Right? So this is not exactly the same as Dedekind cut. This is the countable saturation property. Okay, so the actual Leibniz, the historical Leibniz, was inclined to high orders of infinitesimals. That countable saturation gives you orders of infinitesimality, because if you have an infinitesimal, then also you're going to have infinitesimals relative to it and so on by countable saturation. And Berkeley had complained, some mathematicians, so notably Leibniz and L'Hopital, hold that there are infinitesimal quantities of all orders, and there are infinitesimals of infinitesimals of infinitesimals without ever coming to an end. I mean, Berkeley was complaining about the absurdity of that, but now I'm saying Leibniz is positively asserting that there are these orders of infinitesimals. So Euler also explored vast space of infinite orders. He looked at the functions x and x squared and x cubed, and he looked at square root of x, and he tried to understand how these different polynomials relate to one another with respect to their growth behaviors at infinity. And those ideas led to further work of Hausdorff with Hausdorff gaps and so on, if you know what these are, and the work of Hardy on the orders of infinity. So it's a similar kind of thing. Those structures are countably saturated in exactly the same way. So now let's turn to the imaginary Newton, and I imagine that he's going to say the two number realms fulfill all the same fundamental mathematical laws. Of course, we need these laws. I mean, we want hyperreal numbers. When we're working with hyperreal numbers, we want them to behave like real numbers according to the same rules of distributivity and so on. For example, and this is what I want to write on the board here. If you compute the derivative of x squared, then, well, I mean, using the infinitesimal manner, right, you would take x plus delta squared minus x squared over delta. That's the rise with the run. You know, I'm not going to take a limit if delta goes to 0. I'm just, delta is an infinitesimal number, and I perform this calculation. Well, you expand this out, you get x squared, what is it, 2x delta plus delta squared minus x squared over delta. But the x squareds cancel, the deltas cancel, and you get 2x plus delta. And that's why the derivative of x squared is 2x, because this is vanishing to 0 and so on, the ghost. The ghost of degree, just we let that disappear, and the derivative of x squared is 2x. So we want to calculate with infinitesimals, we want the same rules of mathematics to apply. Both Newton and Leibniz were doing that. Okay. So the hyperreal numbers should be an ordered field, in fact, a real closed field. So every positive number should have a square root, and every odd degree polynomial should have a root, and so forth. So from a contemporary perspective, of course, that's an incipient form of what we would call the transfer principle. The transfer principle is the principle saying that the real field is an elementary submodel of the hyperreal field. And we want it not just for the field structure, but for any extra predicates that we put on. We want to be able to use those predicates and functions, like we want to be able to apply the log function and the sine function and so on in the hyperreal context. And the transfer principle allows us to do that. Okay, so the actual Newton had, in fact, a deflationary attitude towards infinitesimals and fluxions. He wrote that it was just a method of avoiding the tediousness of the old calculation. There's nothing new happening. So they were eliminable, a conservative extension, which is a kind of transfer. It's a kind of hint at the transfer principle if it's saying that the laws are the same, nothing new is happening. Okay. So the thought experiment is that Newton and Leibniz have expressed the idea of two number realms with vaguely expressed ideas that we could now look at as forms of the transfer and saturation principles. That's what I want. I'm not requiring that they have a full-blown theory of the hyperreals with non-standard analysis. That can come in time, right? They just need the vague idea of two number realms with those other vague ideas. But then, of course, rigor comes over the years, over hundreds of years. We would get more precise accounts of exactly the nature. We know for a fact that transfer and saturation are fundamentally coherent and correct accounts of the hyperreal numbers. And furthermore, those ideas are sufficient for a highly successful and insightful development of the fundamental theory of calculus. It's possible, because of non-standard analysis, to found calculus on those ideas. So they wouldn't meet any obstacle if that's the track that they were headed on. For example, you could look at Kiesler's wonderful book. I think it's called Elementary Calculus and Infinitesimal Approach. It's like a intro calc book that you would get in Calc 101. That's not using epsilon and deltas. It's based on infinitesimal numbers and the hyperreal numbers. And if you open the front cover, you see the properties of finite real numbers. If epsilon is an infinitesimal number, then 1 over epsilon is an infinite number, and so on. And it gives you all the basics. And they go on to develop all of calculus using those infinitesimal ideas. So even with very simple ideas at the Calc 1 level, it's extremely robust as a theory of calculus. And there would be no need with that approach to calculus to ever adopt the Bolzano, Weierstrass use of epsilon deltas and so on. Okay. If you consider that in our actual history, even in a completely incoherent account of infinitesimals was extremely successful and led to many discoveries, including all of the fundamental theorems of calculus. So in the old days, they proved all the fundamental theorems of calculus without any proper limits and so on. And they only had this extremely flawed concept of infinitesimal. So I mean, it brings the question, do you need a rigorous foundation for insightful mathematical discoveries of enduring importance? And the answer is apparently not, because that's exactly what we had in calculus. It wasn't a good foundation, yet it was extremely robust and valuable. And they proved all the right theorems, even though their foundations weren't any good. Okay, so in the thought experiment, of course, we get all the actual theorems that were proved with the bad foundation, but it's going to be more correct and it's going to be more rigorous and it's going to, because it's a proper foundation. And so they would get an enduring calculus based on infinitesimals proceeding roughly along the lines of non-standard analysis. This is really what my thought experiment is, that the hyperreals, calculus would become based on the hyperreals in a much more profound and thorough manner than it is currently. So at bottom, the proposal is that the hyperreal numbers would become one of the standard number systems that mathematicians discovered and became familiar with. We have the natural numbers and the integers and the rational field and the real numbers and the complex numbers, but next to them in the thought experiment world would be the hyperreal numbers. It would be one of the standard structures that mathematics was about. So Gödel comes out in favor of the imaginary history. This was at the 1974 conference, I believe at Princeton, the Robinson conference. I don't know if you were in New York at this time, right?
I wasn't there.
Were you?
But this actually is in the preface to the second edition of Robinson's book.
Oh, I see. Okay. So, but it's based on his public remarks, right?
I don't know where he first said it, but it's certainly.
That's what I read. I think, maybe I have it wrong. I'm going to go look it up. Okay. So Gödel says there are good reasons to believe that non-standard analysis in some version of it will be the analysis of the future. And he describes the process by which we move from the integers to the rationals and so on. The next quite natural step after the reals, namely the introduction of infinitesimals, has simply been omitted. We have omitted it. I think in coming centuries, it will be considered a great oddity in the history of mathematics that the first exact theory of infinitesimals was developed 300 years after the invention of the differential calculus. Okay, so what he's saying is that the actual history is weird. It's the imaginary history that should have happened. So I think that's pretty strong support for the reasonableness of the thought experiment world that I'm describing. Okay, so now I want to come to the categoricity part. So Isaacson, taking inspiration from Kreisel, describes the process by which mathematicians come to know their mathematical structures. So we become familiar with the structure, we find the essential features of it, and then we prove that those features categorically characterize it up to isomorphism. So he writes, the reality of mathematics turns ultimately on the reality of particular structures. The reality of a particular structure constituting the subject matter of a branch of mathematics is given by its categorical characterization, the principles which determine that structure to within isomorphism. Okay, so the categorical accounts of our particular structures become the framework of our mathematical reality, is how one might say it. Okay, and indeed, that's exactly how things played out at the end of the 19th century and the early 20th century. Mathematicians began to provide categorical accounts of all of the standard fundamental number systems. So we identify the axioms that are true in the structure such that those axioms furthermore determine that structure up to isomorphism. Of course, usually you have to use second order logic when you're doing that. In light of the Levenheim-Skolem theorem, there's no first order theory that can be categorical in that way for an infinite structure. Okay, so one of the first and most important ones is Dedekin's categorical account of the natural numbers and the theory of the successor relation. So any two models of Dedekin's theory of the successor are isomorphic. So the theory says 0 is not a successor, and the successor function is 1-to-1 and second order induction. So every number is generated from 0 by successor in the sense that if you have a set of numbers and it contains 0 and it's closed under successor, then it contains all the numbers. So that's the Dedekind account of the successor relation, and it's categorical. It determines that structure uniquely up to isomorphism. So using that, mathematicians provided categorical accounts of the integer ring. For the integers, you want to go sort of both ways. There's an inductive version going both ways, or you can take a definition of it as the same difference relation in the natural numbers. There's a lot of different ways to get a categorical account of the integers. The rational field is going to be the quotient field of the integers, and this is going to be a categorical account. So Cantor gave a categorical account of the rational order, the countable endless dense linear order. He proved introducing the back and forth method that any two countable endless dense linear orders are isomorphic. That's a categorical account of that order. Huntington provided the categorical account of the real field. It is the unique complete ordered field. 1903. And the complex numbers can be characterized as the unique algebraic closure of the real field, or you could also characterize them as the unique algebraically closed field of characteristic 0 and size continuum. There's a lot of different equivalent characterizations. Okay, so each of the central structures in mathematics around that time found its categorical account. So these categorical accounts really enable the coherence of the mathematical enterprise in the style that, in the manner that Dan described. So categoricity is what enables us to refer even to those various fundamental structures by their defining characteristics. We don't have to talk about a particular complete ordered field that we built, say, in set theory using Dedekind cuts in the rationals, whether it's a particular construction and so on. We can just say the complete ordered field, and there's only one up to isomorphism. And if we only care about it up to isomorphism, then that's going to be completely adequate. And so for this reason, those categoricity results implement the philosophy of structuralism in a very direct manner. They're connected deeply with the mathematical use of structuralism. And I want to mention this issue that I have observed, namely there's really two independent strands of structuralism. There's this philosophical strand which generally grows out of Benacerraf, I think, and many philosophers are talking about structuralism, the structuralism that's coming out of Benacerraf. But when you talk with mathematicians, and many of them have very strong views on structuralism, and they've thought a lot about structuralism, but almost never will they mention Benacerraf. It's just not part of what they're talking about. Rather, they're tracing their ideas on structuralism back to the categoricity arguments. It begins with Dedekind. And so I think when you're thinking about structuralism, it's, I think, fruitful. I found it fruitful to compare these two strands because they're not often distinguished as much as they might be. Okay, so back to the thought experiment. Okay, in the imaginary history, the hyperreal numbers have become a core structure on the list. The natural numbers, integers, real, complex, hyperreal. And so we would demand a categorical account of that structure. It would be necessary for the coherence of mathematics. Okay, but is it possible? Can we give a categorical account of the hyperreal numbers? And the answer is yes. We can prove a categoricity theorem for the hyperreal numbers. So the final step of my thought experiment is that we imagine a Zermelo-like figure who writes down the theory, just like the actual Zermelo wrote down his axioms in order to give an account of the well-ordered theorem. In my thought experiment world, the Zermelo-like figure is writing down a theory that's going to provide the categorical account of the hyperreal numbers. And he's going to prove the hyperreal categoricity theorem. If you assume CFC plus CH, then there is, up to isomorphism, a unique smallest countably saturated real closed field. So we get categoricity for the hyperreals if we assume CH. Okay, so you can prove this in a back and forth argument. It's similar to Cantor's back and forth argument. So Cantor, for the countable dense linear order, right? You build up the isomorphism in a sequence of length omega using finite partial isomorphisms. And at each stage, you get another point and it fits in with the previous ones. And you can extend the isomorphism to accommodate that new point, and you go back and forth in this way, and get the full isomorphism then. But in this hyperreal categoricity theorem, it's just exactly the same, except now it's a little more difficult because it's a transfinite length construction of length omega 1. If you have CH, then if you have two countably saturated real closed fields of size continuum, size Aleph 1, then we're going to build up the isomorphism with countable partial isomorphisms. We look at the new point we haven't yet handled. It fits with the previous countable points, and we can extend that isomorphism. There's a point just like that on the other side because of saturation, and we can build up the isomorphism this way. So it's just a transfinite generalization of Cantor's back and forth construction. Okay, so we didn't really need very much of the transfer principle. All we needed was that it was a real closed field in order to prove that. Okay, so that's sort of a little bit of what I had imagined Newton to have said. So the theorem in the actual history was proved in 1955, so a slightly stronger version. Under CH, there is up to isomorphism only one real close field of size continuum whose order is countably saturated. So we only need the order to be countably saturated, not the whole structure. And so that's why in fact, they're equivalent anyways. Okay, so in this way, from the continuum hypothesis, we can prove that there's a unique hyperreal structure up to isomorphism. But there's no categoricity result without CH. There's no theorem. If you don't have CH, it's not a theorem. You can't do it. So the first hint of that was shown by Reutemann, who shows it's relatively consistent with the negation of CH to have multiple non-isomorphic hyperreal fields arising as ultrapowers. Those ultrapowers are always countably saturated. So this would be a countably saturated real close field, but they wouldn't be isomorphic under non-CH. But then Alan Dow proved, in fact, it's just equivalent. If CH fails, then there are always multiple non-isomorphic ultrapowers that are non-isomorphic even in the order. The order isn't isomorphic. So therefore, CH is just equivalent to the hyperreal categoricity here. CH holds if and only if there's a unique countably saturated real close field of size continuum. Okay, so with CH, we have categoricity for the hyperreals. Without CH, we lack categoricity for the hyperreals. Okay, so it's very easy to find mathematicians talking about the hyperreals. I Googled on Math Overflow, and there's dozens of occurrences of that phrase on Math Overflow, but it's not actually meaningful. I mean, it's the. What is the? I mean, there's not one structure. Without the categoricity result, you're not entitled to speak of the. And CFC doesn't prove that there's a unique hyperreal structure. So we just said you need the continuum hypothesis for that. So I have argued that the lack of a categoricity result for the hyperreals actually explains in part the hesitancy of mathematicians to do non-standard analysis. So the epsilon delta approach to calculus and non-standard analysis, sort of two alternatives, and there's definite hesitancy. And okay, you can explain a lot of the hesitancy by upbringing, because we all learned the epsilon delta approach and so on, and so it's a cultural phenomenon. Because mathematicians who later learned the non-standard analysis approach, like it and find it a formula. Of course, we can translate back and forth, and so maybe it doesn't matter that much, but there is a definite hesitancy to adopt the non-standard analysis, and part of that reason might be that it's a bit incoherent to base this whole theory on the hyperreals if the hyperreals are not a thing. It's many things. Which R star are you going to use? And they're not all isomorphic in general, right? Which one do we use? How can we even describe which one to use? We can't pick any of them out by a property that they have because there is no categorical account. Okay, so the lack of categoricity leads to a kind of lack of reference. Okay, so the thought experiment at bottom is that the hyperreal field has become a core idea present from the beginning and essential for calculus. Calculus would be based in the non-standard analysis manner on the hyperreals. At first in a pre-rigorous manner, but then with increasing rigor and sophistication. And eventually, mathematicians demanded categorical accounts of all of their structures, and this would be required also for the hyperreals. And it's possible to do that, but only if you have CH. Okay, so this is how CH gets on the list of fundamental axioms because it's a necessary part of providing meaning in mathematics and even at the level of calculus. It's indispensable for the foundations of calculus. Okay, so of course that's an extrinsic justification for CH. We get enormous extrinsic support for CH because of that desired consequence of a categorical account of the hyperreals. But of course, right, okay, so I'm sorry, it's similar to a way of thinking about CFC. CFC provides an enormously successful account of the real numbers. And it's proving so much of what we want to prove about the real numbers. We can prove the categorical account in CFC and much, much more. So similarly, CH would be seen as vital for the account of the hyperreals in the thought experiment world. Okay, knowing human nature, once you have extrinsic justification, then of course mathematicians would find it very easy to rationalize intrinsic justifications in a manner that arguably has occurred with other axioms such as the axiom of choice. Axiom of choice maybe at first is viewed with extrinsic support, but now I think it's quite common to take it as having enormous intrinsic support. So many people, myself included, take the axiom of choice as something close to a law of logic, which is a way of saying that it has intrinsic support. Okay, so I'm imagining maybe one of the forms of intrinsic justification would go like this. The continuum hypothesis, which is definitely true because it's needed to provide the hyperreal categoricity theorem, okay, is obviously true because it unifies the two methods of producing uncountable infinities. So on the one hand, I mean, CH is equivalent to the identity of Aleph 1 and Beth 1. And the Aleph 1 is one way of getting to a larger infinity in the Hartog manner. And the other one is the taking of the power set. And to unify these two accounts of the uncountable is equivalent to CH. So that's possibly, okay, speculatively a intrinsic justification. Okay, a critic maybe wants hyperreal fields of larger cardinalities because the hyperreals I was talking about were just the ones of size. Continuum, okay, we can satisfy that critic. If you assume ZFC plus the generalized continuum hypothesis, then you can prove that there is up to isomorphism a unique saturated real closed field in every uncountable regular cardinality. So we get hyperreals at the level of Aleph 2, Aleph 3, and so on. All the regular cardinals are going to have their hyperreal field at that level. And in fact, that is equivalent to the existence of those saturated models is equivalent to the generalized continuum hypothesis. Okay, so we have this sort of tower of infinitesimality continuing to all the higher cardinals. And I take that as a kind of natural continuation of these saturation ideas that Leibniz and Euler, Hausdorff and Hardy were thinking about that I mentioned earlier. So we're just looking at sort of higher levels of those ideas. Okay, ultimately what we get is those hyperreal fields of all the different cardinalities would form an elementary chain whose union is the surreal numbers. So it's going all the way up to the sort of proper class sized fields. Let me turn to a slightly different topic. So Tim Williamson has speculated on how it would be that other beings with physical and mathematical powers similar to humans might settle the continuum hypothesis. So he introduced the concept of a normal mathematical process and said one normal mathematical process is adopting a new axiom. And if set theorists finally resolve CH, that is how they will do it. Of course, just arbitrarily assigning some formula the status of an axiom does not count as a normal mathematical process because doing so fails to make the formula part of mathematical knowledge. So in particular, we can't resolve CH simply by tossing a coin in order to determine. Right. So we want to know whether it holds not merely to have a true or false belief one way or the other, And the question arises, when does acceptance of an axiom constitute mathematical knowledge? I believe that my thought experiment engages with the Williamson's challenge in that regard, because the people in my thought experiment world are not flipping a coin to decide. They're choosing CH for a sound mathematical reason that I've described the richer context and process that would lead mathematicians to CH. So they would introduce it as an axiom because it enables them to prove this absolutely required result, the categoricity theorem for the hyperreal numbers, which is necessary for the coherence and reality of their practice. Okay, so I take them to be undertaking in accepting that axiom, the normal mathematical process. Maddie has written on the contingency of ZFC, because the very situation of my thought experiment is that ZFC is contingent. If history had been different, we would have different axioms. She says, the fact that these few ZFC axioms are commonly enshrined in the opening pages of mathematics texts should be viewed as a historical axiom, not as a sign of their privileged epistemological or metaphysical status. Okay, she was mainly concerned about extensions of ZFC by large cardinals, not about the kind of extension I'm talking about. But it is another kind of historical contingency showing how we might have taken CH as a principle. The discovery via forcing that there could be multiple non-isomorphic hyperreal fields. Right? I mean, with forcing, we can make not CH happen. And in those models, there would be multiple different non-isomorphic hyperreal fields. I think that would just, in the thought experiment world, be seen as bizarre and chaotic. It would be a little bit similar to the situation that we know happens now. If you drop choice, it's possible that there are two different algebraic closures of the rational field. Normally, when you have the rational field, you can take the algebraic closure of it. These are called the algebraic numbers. There's only one up to isomorphism. This is the standard result. But you need the axiom of choice to prove that theorem. Actually, it's consistent with ZF that there is a countable algebraic closure of the rational field, as well as an uncountable one, which is completely bizarre. And if you ask mathematicians about the algebraic numbers in these models of ZF, the reply that you usually get is that those models do not understand the algebraic numbers. They have a wrong theory of what the nature of algebraic numbers are like. And I think a similar thing would happen. A similar view would happen in my thought experiment world about the models where CH was failing, where you had multiple non-isomorphic hyperreal fields. They would be seen as weird and bizarre, and that those models do not understand the hyperreals in exactly the same way that we think about this Lockley result as weird and bizarre. Okay, I think in the imaginary universe that I'm describing, forcing would be seen as a little bit less successful precisely because it doesn't preserve the fundamental theory. One of the important things about forcing is that if you have a ZFC model and you go to a forcing extension, you still have ZFC in the forcing extension. But if your basic theory is ZFC plus CH, it's no longer true that every forcing extension still has CH. So the basic theory isn't preserved. So it would be something, I think those models maybe would be viewed in a similar way that the symmetric model construction is viewed in today's world. I mean, symmetric models is a manner of building models of ZF that don't have the axiom of choice. And in particular, you can build some really badly behaved models in which choice fails, like the Lockley model and so on, the other models where choice fails, or where you have, amorphous sets or infinite sets that are not Dedekind infinite and so on. So these weird models where choice fails are constructed with this method called symmetric model construction. And I think the attitude that mathematicians and set theorists have towards those models, it's a way of building weird models would be shared by forcing in general amongst the ones that don't preserve CA. Okay, so let me just kind of wrap up here. My thesis is that we could have had a very different perspective on the continuum hypothesis. Early mathematicians could have been clearer about infinitesimals, positing distinct number realms. The hyperreal numbers would have become a core structure of vital importance in calculus, woven into the heart of calculus. all core structures require a categorical characterization for meaning and reference. Okay, but a categorical account of the hyperreals is only possible with CH. It's possible only with CH. And therefore, CH would have been part of our foundational theory. It would have had extrinsic justification because of that, and in time, intrinsic justification. We would have viewed CH as necessary for mathematics, indispensable even for calculus. So that's it. Thank you very much.
I've got a 5-minute break and then return for Q&A.
Okay, great.
Okay, so let's get started with the Q&A. During the talk, there was a question from Alan Slomson, or at least it looked like maybe there was. I don't know if Alan is here and would like to ask that question, but others who may have questions, put your hand up and I'll take notes. We'll just, maybe he's not here right now, so I'll come back to him later. So Wes, why don't you start us off?
Well, thanks very much for the talk. Really, really fascinating stuff. Actually, my question is really just about sort of what makes this a kind of alternate history, or maybe the question is sort of how it fits in with your own view of CH. Because I mean, you mentioned the Gödel quote, and that seems to have some normativity built into it. Right? This is how things should have happened. In the future, people will see that they've gone wrong, right, and we'll have that. So I suppose, yeah, maybe my question is just why isn't this a really nice argument for CH? I take it can't be on your, on your view, but yeah, why, given that history didn't happen the way you described, why shouldn't we go back and correct it? And yeah, we actually do need a categorical characterization. We'll just adopt CH. You've got the dream solution, breakthrough done.
Right. Excellent. So that's a really good question. So you're totally right. I mean, I think I agree with you that there's this normative aspect of Gödel's view on that matter, that the history should have been like that. Whereas I'm really only arguing that it could have been, and it wasn't like that. And so for this sort of contingency about CFC as the fundamental theory could have been different. So maybe there's a lot of different ways. Maybe we could have been better with type theory in the early days, and set theory would be this sort of niche thing, and we would all be doing type theory in a much more rigorous way, and so on. And I'm not sure how to answer the question about the connection with pluralism, though, because I mean, of course, if you're a monist, then you think that there is an answer, and so if you think that it could have, that it could have been a fundamental axiom, then that's the same thing as arguing that it is a fundamental axiom. If you're, if you're a hardcore monist. And so in a way, the thought experiment argument is talking with the monists a little bit, but I'm not going as far as they are. I mean, if they accept this argument that it could have been a fundamental axiom, then on the basis of the monism, then they would deduce that it is already a fundamental axiom, whereas I'm not making that final step. But I still think it's important to realize that we could have this different way of thinking about CH as a fundamental axiom, which I think is interesting, and I think it is shedding light on how we should think about some of these issues. So I'm sorry, that's not a very good answer, but
no, I think that's helpful. Thank you.
Sure. I was going to ask the question, so I'll ask a follow-up, which is, how much room is there as a pluralist to say that following this path would have been better, if not the right answer, at least better? How much sort of flesh can you put on that boat? Because that seems to be quite a tempting conclusion, that it would have been better to go this way.
Oh, I see. Yeah, that's not at all how I was thinking about it. So that's quite interesting that you say it's tempting. I mean, I don't think I was trying to hint at that conclusion, rather.
Well, at least I'm tempted by the way. I'm accusing you of this sin, I suppose.
I mean, I think rather the lesson that I would like to take as a pluralist from this kind of, if the thought experiment is successful, then I would want to look, well, what other kind of theories can we give similar kind of reasonable seeming accounts for that we would arrive? For example, is there a similar kind of thought experiment where you would arrive at not CH? And maybe there would be something about some fundamental thing requiring a distinction between the bounding number and the dominating number or something, and that the ideas would only make sense if CH failed. And so, I mean, I can imagine such kind of, I don't know any successful such arguments, but it would seem that the pluralists might be tempted to kind of give a lay of the land. What are the possible situations that we might have found ourselves in? And that would be a kind of pluralist undertaking, right? To investigate all those different possible fundamental axioms that we might have been led to for similar kinds of reasons with sound motivations.
Yes, I agree with that. So I forgot to say, if somebody has a question from the online portion of the meeting, let us know in the chat or put your hand up as Daniel has done. And I will call on you as I will call on Daniel right now.
Hi. Yeah, I mean, I love this paper and this talk, and I guess I had a follow-up to the first question, which is, what would you say? So I'm tempted to think of this, in a certain frame of mind, where I find this to be a compelling argument for CA. I then start to think that what you've done in this paper is provide a kind of error theory about how it turns out that adventitious historical developments can sometimes shape in profound ways what we accept. We know that this is the case independently outside of mathematics. So a lot of the content of specific religious traditions is not something, is very widely accepted, devoutly believed. I mean, a paradigm of devout belief, but in fact, often contingent on historical developments that need not have occurred. And sometimes it's surprising to think, but this does happen. So analogously, in this case, what we have is a reason to think that for specific contingent historical reasons, we are in a situation where we regard the question of CH as deeply open, but we have now an explanation of how this need not have occurred, and we can, yeah. So what do you think of that kind of diagnosis of what this historical story is doing?
Right, I guess that's basically what I'm trying to argue for with the contingency, the historical contingency. I mean, I think that much of what you said resonates with what I'm saying. I mean, for example, one can easily imagine that, say, Brouwer and Bishop had been more successful in their arguments, and that mathematicians were tempted more to found more mathematics on, constructive approaches and explicit computation and so on. There would be a kind of different culture of mathematics in such a way that it would be more strongly founded on intuitionistic logic and constructive axiom systems. And that would be another example of the kind of historical contingency for the axioms. So CFC in that kind of thought experiment world would be rejected and replaced with more constructive analogs. And I guess there's probably quite a lot of other instances of such kind of situations that you can imagine, and maybe give some legs to those thought experiments that would make you realize that the list of axioms that we have written down is contingent in exactly the way that you were describing.
All right, thanks. That's helpful, thanks.
So do you want to stop sharing your screen? Then we would see more of the Zoom
okay,
participants.
sure, yeah, I can
And
do
you
that.
can bring it back if it's needed.
Like this? Right.
Oh, we can-
Yeah, no, it'll go to the next speaker.
Daniel turned his camera off. Okay, Beau?
Yes, thank you. So that's really interesting. This, I think I was going to ask Wes's question, so I will make this just kind of a follow-up to that. I think that the universalists can take on board a great deal of this methodology and, properly understood, can assent to your claim that in a certain sense that this could have been a fundamental axiom as long as we, leave open whether we're taking that description of practices in a factive sense or not. Because, what I think the universalists will say this demonstrates is that rational mathematicians could have been, who progressed through a certain historical trajectory, could have been in a position where they had very strong reasons for believing CH and not particularly convincing reasons for believing not CH. But that of course is compatible with thinking, but that's compatible with thinking that there are other trajectories on which the reasons could have come in a different order. It seems, like for any really complex question for which there are, interesting and difficult arguments on both sides, it seems really plausible that we can think that there could have been rational inquirers who encountered those arguments in a certain order that would leave them at the end of it such that they had very strong reason for believing P as opposed to not P, and vice versa. That's surely compatible with there being a fact of the matter as to it. We should admit that people can sometimes have very strong reasons for believing things that are nonetheless false. So I'm just saying, I think that like nothing you've presented here is anything that the universalist has to reject as an investigative methodology.
Right. So that's interesting. Thank you. Well, let me just try to push back against it a little bit. So, if you think about, if you have the universe point of view, so set theoretic monism, there's the one true set theoretic universe. And you imagine the thought experiment of the people who became obsessed with the hyperreal numbers in the calculus, and they insisted that calculus be done that way, which is like maybe a slightly more disparaging way of describing my thought experiment, right? So much so that those people required CH in their fundamental axioms because that's what it took to get the categoricity result for the hyperreals, which is what they thought was important. But mainly, we already know, so do we really need a categoricity result for the hyperreals in order to make sense of mathematics? Well, no, because we are, in our actual world, we don't have that theorem. It's not a ZFC theorem, and we do calculus fine, right? And let's imagine that Woodin's arguments for not CH based on omega logic are successful in that we're universes with the one true set theoretic universe, but we're getting not CH. And if that were true, then we would have reason to look at those thought experiment people and say, look, they got the truths wrong. They thought CH should hold because they were obsessed with hyperreals, but actually we know because of omega logic that not CH should be the case. And so this would be a way on the universe view of saying that a way of criticizing the thought experiment we're not being reasonable, right? If we had reason to think of not CH, then we should think that they were wrong to found calculus on the hyperreals and insist on a categorical account because that requires them to deny the fundamental axiom of not CH. So isn't that a way of pushing back at your suggestion that somehow it's automatically compatible with the universe view? Because in this way of thinking, I think it wouldn't be compatible. If you're a universe view and you are agnostic still about CH because you don't yet know, then I agree with you that you could take the thought experiment as maybe possible evidence that maybe CH is true in the one true set theoretic world. And because of omega logic, maybe not CH is true and we still don't know. So that's a sense of it being compatible, and I would agree. But I could imagine that if one of those sides, was more successful, it would be grounds for rejecting the reasonableness of the other side.
Well, it would be grounds for thinking that they have a false belief.
Right.
And I can think that, Newtonian mechanics is a false theory, but nonetheless think that it was extremely reasonable for people in the 17th century on the basis of the evidence they had to think that it was correct.
Oh, I see. That's really interesting. I like that a lot.
So, this is just like treating it in the same way we would treat any other disputed factual question.
Right. So the question would be, what is the fact of, if you're amongst universalists who believe there's one truth, there's a fact of the matter about CH, then what does the thought experiment say about this fact of the matter if we disagree? That's quite interesting.
Marcus Giaquinto.
Hi, thanks for an extremely interesting talk. Can I be heard?
Yes.
There's just one thing that worries me about your argument that we could have easily adopted CH in this counterfactual world, which is, well, at some point you acknowledge that to do calculus with infinitesimals, you don't need the categoricity of hyperreals. You don't need it. You just need the transfer principle. But later on, towards the end of your talk, you said that categoricity was necessary for the coherence of the practice. And that, I think towards the end, you were making a stronger case for it than there really is, because you don't need the categoricity. And you, of course, as you pointed out, you don't have it in Robinson's non-standard analysis.
Right, that's absolutely right.
All you need it for is for to justify mathematicians or others who talk about the hyperreals. I mean, you can. It's just a small mistake, and it's not a big deal. So this need for CH, which rides on the back of the supposed need for the categoricity of the hyperreals, it's a weak point, isn't it?
No, I don't agree. And I tried to argue at length about that. This is what section 4 was about when I'm talking about Isaacson's views on categoricity as extremely important. I totally agree with the mathematics of what you're saying. You can do nonsense analysis without categoricity, and that is how it's done, because we do it in CFC, and we do it with one hyperreal field, and we don't really care which one it is, even though they're not isomorphic. But nevertheless, I view it as a sort of core mathematical demand that all of our fundamental structures should have categorical accounts. And that's the part where I'm saying it's essential. It's essential for the meaning and the reference of our mathematical activity, the reference of the terms in our mathematical activity, and for the meaning of these structures. And so I'm looking at the practice of providing categorical accounts of our core structures is vital. And as I'm taking Isaacson to argue, so sort of relying on that part, so not just on the practice of non-standard analysis, which I agree does not require categoricity, but rather it's this philosophical demand for categoricity in all our fundamental structures. I mean, one could ask, well, do you need categoricity of the real numbers to do real analysis? I mean, suppose that there were, in some sense, multiple different real number systems. I mean, as there are, for example, in intuitionistic logic, they have the Dedekind reals and the Cauchy reals and so on, and they're not the same. And the theory is a mess. Because of that, they have to be constantly saying what kind of real numbers they're talking about and which system they're in and so on when they're doing the arguments. And so the fact that we have categoricity for the real numbers is extremely helpful for our mathematical understanding of what's going on in that subject. And I would claim the same would be true in calculus if it was founded more thoroughly on the hyperreal numbers. We would also want that kind of situation in the calculus founded on non-standard numbers.
Yes, go. Go, Marcus, please.
I mean, we only knew that these we only people had some grasp of the rational numbers before they started thinking of them as the smallest field containing the integers. And the same with the real numbers. I mean, people were operating with them and had some familiarity with them before they were conceived of as the completion of the rational numbers. I mean, really, all that came in with Dedekind, but the use and understanding of those other number systems was already there. Without, yeah, you know, without, yeah.
I mean, sure, that's true, but you can't deny that the categoricity result for the real numbers is seen as a core foundational result in real analysis. It's theorem one in, you know, I don't know for effective it's theorem one, but okay, it's a core theorem at the beginning of any book on real analysis, proving that the reals are a complete ordered field. It's a core part of our understanding of what's going on in the subject. And so even though it's possible to do real analysis without having that categoricity result, which I totally admit, you're totally right about that. That result is providing a fundamental unity to the subject in a way that's extremely welcome to mathematicians. And I think that if we were doing a similar kind of investigation in calculus using hyperreals, it would serve a similar role. It's possible to do it without, I totally admit that. But I think it would be an extremely welcome and seen as a fundamentally important result in the subject to know that you have a categorical structure.
So we have a lot of questions, so I'm going to skip the follow-up.
Oh, sure.
Okay.
Sure.
You're on my list, don't worry. So next up is Benedict.
So universes, generally I take it aren't universes because of the state of their current set theory of practice. So there's something promissory about that position. Whereas I understand that your argument for pluralism sort of takes it as a premise that we should take current set theory of practice quite seriously. But so it seems like there's a kind of asymmetrical upfront with this tool. Perhaps we shouldn't take the current practice as seriously as you're sometimes take in your argument. Whereas universes can say, well, the fact that there are near possible worlds in which we have very different conception of the set doesn't really threaten my perception of how we should answer these questions.
Right. Thank you. Well, I don't really take myself to have been arguing for pluralism in this talk. Okay, that's fine. So I think you're right about the universe is not basing their views on current practice, but rather there's this sense that that the concept of set is clear enough and that that it has only one meaning and it gives rise to the one true set theoretic universe. And that's the kind of idea I think that's motivating those who have the universe view. Whereas if you're denying that, you need to explain, well, how, what are these different concepts of set that might have given rise to the alternatives, right, for a set theoretic pluralist. And one way of doing that is to look at, the different set concepts that we've built in our current practice. We have forcing and so on and intermodals and so on. We've built all these different models which are naturally interpreted as alternative set concepts. And so it's not that you're being led to pluralism because of practice. It's rather just that the current practice is providing you with this abundant array of alternative set concepts. And it seems like there's an abundance of alternative possible concepts of set, and each of them would give rise to their own set theoretic universe. Okay, and then when you combine it with this kind of historical thought experiment way of thinking, then I suppose it's just leading even more to alternative ways of thinking about what we might take as alternative set theoretic universes or alternative set concept. So it's connected with sort of looking at practice. My argument on the dream solution, on the other hand, is explicitly appealing to this kind of sociological phenomenon that you mentioned, namely, I argued that we can't have a dream solution of CH because we've already become familiar with the set concepts in which CH is true and the other ones in which it's false. And they both seem totally set theoretic and completely reasonable. So if you have an axiom that's implying not CH, then I can't accept it as a fundamental principle of sets because I already know what it's like to live in a world where the opposite hypothesis holds. I can't accept your assertion that only Brooklyn exists because I've been on Fifth Avenue in Manhattan and I know it exists and it's a perfectly reasonable place. So that's a kind of sociological argument, right? If you think about how does the dream solution argument work in my thought experiment world, I think it's interesting to consider that because in that thought experiment world, they wouldn't have had that experience in the not CH worlds. They would have had CH as an axiom and they would have looked, I argued explicitly that they would have looked at the not CH worlds as weird because those are the worlds where you don't have the correct theory of the hyperreals. You have these weird multiple non-isomorphic hyperreals, which is bizarre in the same way that having multiple algebraic closures of Q is seen as weird. And so they wouldn't accept the dream solution argument. They would have said, look, the CH is true because we use it to prove the hyperreal categoricity theorem. So in a sense, in that world, the dream solution method is successful. Right? They're sort of inverted though. They're not assuming an axiom to prove CH, but rather they have this strongly desired conclusion, the hyperreal categoricity theorem that they want to prove, but the only way to prove it is with CH. So, but it's similar to adopting the dream solution.
Michael Collins.
Well, thank you. I'm going to take you off on a slight tangent, if you don't mind, Joel.
Sure, that's fine.
I want to warn everyone else that I'm a pure algebraist and not in any sense a logician. I was fascinated by the one comment, which in fact you just brought up in your last answer, and that is about the algebraic closure of the rationals. Because what you've said is that you need the axiom of choice to prove essentially uniqueness up to isomorphism.
Yes.
If you just took ZF and threw in the continuum hypothesis, but not the axiom of choice, what would the outcome be? Because if you could not prove, or more to the point, if you could prove there are multiple models, then that would imply that the continuum hypothesis does not imply the axiom of choice. And this takes me back to, and I say, declare my age in the process. The Cohen's theorem was the big thing when I was an undergraduate.
So thank you for the question. That's quite interesting. If you have ZF, if you don't have the axiom of choice and you're working in ZF, then you have to be a little bit more careful about what you mean by the continuum hypothesis, because the statements that are equivalent in ZFC are not equivalent just in ZF. For example, one way of saying the continuum hypothesis is that the reals have size Aleph 1. This is just one of the standard ways of saying CH in ZFC. But it's not equivalent to the statement that there are no infinities between the naturals and the reals. In ZF, you cannot prove the equivalence. For example, the axiom of determinacy proves that that's incompatible with the axiom of choice, but it proves there's no infinities between the natural numbers and the reals. Every set of reals is either countable or equinumerous with the whole reals. But it doesn't prove that the reals have size Aleph 1 because they're not well orderable under AD. And so that's a situation where the continuum is not Aleph 1, and yet there are no infinities between the natural numbers and the real numbers. So if we take the sort of strong form of CH, that the assertion that they're well ordered of size omega 1, then I strongly believe you can prove the uniqueness of the algebraic closure of the rationals. I think I'd have to think more about it, but I suspect that's true. but my suspicion also, I'm sorry, I don't have proofs of either one of these. It's just a kind of intuition. But if you can well order the reals, then I think you could use that information to provide the isomorphism that you want between the two algebraic closures of Q. But if you only have that there's no infinities between the natural numbers and the reals, then I don't really see how you would be able to prove that. In fact, maybe in Lockley's model, in which there are multiple algebraic closures of Q, maybe he even has the CH in that form, in that model. I'd have to look it up, and I don't know the details, but it's quite interesting question. I mean, the other related question is that the generalized continuum hypothesis, so if you know the generalized one, then it implies the axiom of choice. So if you just have CH, you're not going to get any choice from that unless you have the strong form of it. As I said, then you get choice at the level of the reals because you can well order it. But if you have the GCH, then this implies AC. So I don't know.
So I was just going to say thank you. It seems to me this points to the fact there may be a lot of other interesting questions in the area of the relationship between the axiom of choice and the continuum hypothesis, or the lack of a relationship between them. I suppose I was being pedantic.
Right. Thank you very much for the question.
All right. Thank you. So thank you. Oh, I'm very much in agreement, as you indicated. And I think it's a very exciting development. I would be inclined to want to go further than you are and see it as a basis for taking the continuum hypothesis as true. It certainly is akin to a development, but I think then one has to wonder about what's the situation when forcing came to be used. I mean, you might even say, well, it's lucky we didn't have that attitude, because then Cohen wouldn't have bothered to find the forcing notion, and then we wouldn't have had all this wonderful mathematics. However, I don't think, and I wonder about your thought about this, I mean, I don't think that's the case. I think that there is a long tradition, I mean, it's a long practice in mathematics, that when you find axioms for theories, you want to know whether they're independent. And so you have that in set theory. I mean, the whole business of showing that the axiom of replacement is independent from from separation and so on. I mean, those developments and when can choice be proved and when it can't be, those are very important mathematical developments. So I do think that it would have still been important to develop forcing as a means of establishing that, as it turned out, the continuum hypothesis is not provable from the other axioms. But I don't think that counts against, and indeed it counts in favor of taking the continuum hypothesis as an axiom. I mean, just a thought about what you're...
Yeah, that's really quite interesting. I mean, the way I understand your remarks, I was trying to hint at it earlier, which is that if you're a set theoretic monist, which I take you to be, and you think that it's possible that CH is a fundamental axiom, then you have to think that it is a fundamental axiom. And I think that's basically the argument that you just gave us, right? And that's, a step too far for me, but I think your other remarks are really quite interesting. So, for example, another case would be, say, the parallel postulate in geometry. We want to know, is it provable from the other ones? And that's a case where, in asking the question whether it's possible in geometry that the parallel postulate is false, you're led, of course, thereby to non-Euclidean geometry, which is exactly undermining the monist perspective, because that development is exactly what gave rise to geometric pluralism, right? I mean, we have the Euclidean and the non-Euclidean and so on, all the others, precisely because of that kind of activity of looking at whether the axiom was provable or not. And so if you're right about how things would work in the thought experiment world, that the mathematicians would say, well, well, can we prove CH from the other axioms? And then they would develop forcing and so on and prove that no, they can't. But then they would discover these other set theoretic worlds where CH was false and so on. And so maybe this would undermine the monist perspective in exactly the same way that it did in geometry. And so maybe that's one development that would happen, or it's one way of making sense of that kind of activity. I think it's really quite interesting.
I mean, on that parallel, I think one might consider that there was the huge question for several thousand years: is the parallel postulate provable from the other axioms? When it was the demonstration that it wasn't came later after the development of non-Euclidean geometry, but we can reorder the developments as we like conceptually. But in the end, you get a situation in which we see that the parallel postulate is true in the geometry of the plane, and then we have these other geometries, and I would suppose then one could say that the situation in set theory would be that we find that by the categoricity theorem, the Erdős and others' categoricity theorem, we see that the continuum hypothesis is a true axiom for that mathematics, and then you can consider other mathematics, the mathematics of other structures, and as you do in geometry, use negations of the parallel postulate for those theories as you can in set theory. It does seem to me unclear, or maybe it's just ignorance, but I don't think that in set theory we have the situation of the non-continuum hypothesis set theories having the conceptual clarity that the non-Euclidean geometries have, and indeed not the applications either.
Well, we just have many more models.
Yes.
And so, there's comparatively few geometries.
Yes, which is a plus.
Oh, I see. So it's easier to be a pluralist if there's just very few worlds, which is a kind of universe way.
Well, there's a conceptual clarity in that situation.
Right. No, I agree. But about this idea that we should always be seeking independence for our axioms, I think this is often mentioned, but I think sometimes exaggerated, because it's not always true. We have many theories where the axioms aren't independent, including some of the standard foundational theories like piano arithmetic. The induction axioms are not independent. They're rather a hierarchy that's increasing in strength. Sigma 2 induction implies sigma 1 induction and is implied by sigma 3 induction. And so there's huge redundancy in the standard axiomization of PA. And the same thing happens in ZFC with the replacement axiom and the separation axiom and so on. If you think of sigma n separation, this is a hierarchy. It's a scheme of axioms that are getting stronger and stronger and therefore are not independent. You could make it independent by taking the extra part and subtracting off the earlier part, replacing the axiom with either the other one fails or we have this great thing. And if you do that with all of them, then I think they become independent technically, but that seems extremely artificial, and the natural way to look at it is in rather a non-independent, increasing hierarchy of strength. And so I don't agree that we should always seek this kind of independence in our fundamental axioms, because the main foundational theories don't have that feature.
Independence of axiom schema is a different matter.
Oh, I see. If you think of the schema as one axiom.
Yes. And then it's not independent.
Yeah, that's true.
Okay, sorry. Thank you.
Sure.
This is sort of been skated around a bunch of different questions, but I'm going to sort of go at it again in some sense.
Okay.
So I guess if you were honest, obviously you're not, but if I'm honest, then which just a certain style of argument, which is sort of okay, so suppose that P could have been indispensable to turn that into practice, and lot P could not have been indispensable to turn that into practice, then perhaps there's an absolute argument for P. Now, I'm not saying that this is true for CH, and to suggest some reasons why it might not be true for CH. But I just wanted to ask you, like, how powerful do you think this sort of straining argument might be if you were?
Say it again, how powerful what?
About my sort of this type of argument be for oneness, and how, like, what do you think its limits are, and that sort of thing. Like, it's comment on.
Right. So that's very good. I think it's important. I mean, I would really like to have a similar thought experiment for not CH. I mean, that would be great, but I don't have one. I don't have any argument that there isn't one. But I could imagine, you know, some kind of focus on, I guess, let's see. So I gave an argument in my multiverse paper about what I had called the power set size axiom there, where, so the argument was, maybe, let's see if I have to remember the details of it. People looking at, the symmetric groups on sets of different cardinalities. So you can take, for any set of a given cardinality, you can look at the group of permutations of those elements. And if you have a bigger set, you get a bigger group, right? But it's not actually always bigger in cardinality, because it could be that 2 to the kappa equals 2 to the lambda, even when kappa is smaller than lambda. So the size of the symmetric group is 2 to the kappa. So maybe you have some naive argument that the symmetric group on kappa is not isomorphic to the symmetric group on lambda when they're different, because they have different sizes. And so maybe someone's gonna want the different sizes of, you know, the power set to be injective, right? Okay, so I can imagine maybe there's some kind of argument like that that's going to make us land with not CH. I don't know any argument, but maybe there is one. And that would be a way of addressing this symmetry, and maybe it would be, it might be a rebuttal to the universe view argument that this thought experiment is a proof of CH, a philosophical proof of CH, right? If there was an equally compelling thought experiment that was landing you at not CH, then we would know that, well, look, we can either have a categorical account of the hyperreals, or we can, you know, XYZ, whatever it is in that other explanation that I don't know what it is. So does this kind of dichotomy happen in mathematics? I don't know. I'm not sure, but I would love to find out if I could.
So I think you've provided a very convincing account how CH might have become a basic axiom. But I can imagine a second chapter in that history where we lose CH again as an axiom, because some mathematicians are interested in a minimal axiomatization.
Right.
And I mean, this has been said before, you can develop analysis without CH, and well, between that, let's say the criterion would be our basic axiomatization of mathematics is the minimal one we need so that 99% of mathematicians can develop their own mathematics in that framework. So and then in that second chapter of that history, we would lose CH again. And I think there's evidence for that in the actual history of mathematics. So I believe that Grothendieck, he wanted, if we have inaccessible cardinals, to develop his type of algebraic geometry. But I guess nowadays, algebraic geometers prefer to not assume that. And let's say the Stacks project, which is now used as sort of the main reference for algebraic geometry, it does not assume the existence of inaccessible cardinals. So what we would give up is categoricity in favor of having a minimal axiomatization. So I guess my claim would be any history counterfactual knot would converge to ZFC, assuming that, let's say, the composition of mathematicians is roughly the same and care about roughly the same things. So that's why we wouldn't lose CH, the axiom of choice, because algebraists wouldn't have a basis for the vector space.
That's a very good remark. So I address a little bit of it in the paper where I talk about exactly this issue. I mean, I don't make the conclusion that you make, though. For example, if you think about CFC in current mathematical practice, there are many, many pockets of communities of people working in much, much weaker systems. For example, in constructive mathematics, they don't even use classical logic, right? And they're working out the nature of constructive mathematics, or in homotopy type theory or whatever. In these weaker systems, they are working in the kind of weaker system that you're talking about. And yet, for most of mathematics, CFC is a kind of default foundation. And so I would expect in my thought experiment world that, of course, people would be working in the theory without CH, and they would be developing the consequences just of CFC alone, or even much less. In the same way that constructive mathematicians today are working out the consequences of those weak foundations, or maybe they're using, Kripke product set theory or CFC minus, or any of the other extremely weak theories that we have available. Of course, they would be investigated. I'm not quite with you that somehow mathematics always converges to the minimal theory. I don't think that's true. I mean, it's obviously not true because CFC is a quite standard axiomatization, and it's far beyond what's needed. And even though this work you described about abandoning the universe axiom in algebraic geometry, I think it's still quite standard, though, to talk about universes. I mean, it's all over Math Overflow, for example. It's really quite common, and people have questions about it. So it's not like the universe axiom has been abandoned in that subject. I don't think that's true. I mean, people still use it and talk about it, even if this work that you mentioned doesn't happen to do that. But maybe it's also something like in large cardinal set theory, where at any moment, if it is ever convenient or needed to assume a slightly larger large cardinal, then you just go ahead and do it. That's the practice. And so I think if the algebraic geometers ever needed a universe, then I would fully expect them to say, well, okay, let's give ourselves a universe and then maybe another one on top of it. And that would be, I think, probably pretty standard practice. So I'm not sure that it's correct that we always converge to the weakest theory. That's not what we're observing in mathematical practice now. And I wouldn't expect it in my thought experiment either.
Alex.
Thanks very much, Joel. So I had a sort of historical question. So I want to know a bit more about why you assume there was sort of no, you imagine this imaginary world in which there's, real analysis ends up looking a little bit different from Newton and Leibniz onwards, the hyperreals. But then somehow there's no interference from that development. And in other areas of mathematics and the development of set theory and external representativity. I would say this is sort of a very naive historical question, but if we imagine this alternative world, wouldn't it be a sort of knock-on effect on the rest of mathematics? Would ZFC, as we know it, still have been developed? What do you think? I was expecting you to fill in that bit of the story, but you change one thing quite radically and the other thing is exactly the same, and you see no connections between them whatsoever.
Oh, I see. Yeah, that's a very good point. Well, I mean, I guess the Zermelo-like figure that I was imagining that provided the hyperreal categoricity theorem was using CFC plus CH. So, I mean, of course, I was sort of assuming that in the thought experiment world also we would have the categorical accounts of the reals and so on, but this doesn't require CH. You can just do it in CFC. And so that kind of in a sense, I mentioned that one can view CFC as providing the successful theory of the real numbers, and you only needed the CH extra bit in order to provide the categorical account for also the hyperreal numbers. And so I'm not sure that there would be a kind of tension. It's not it's just this add-on axiom, but the rest of the CFC development, why wouldn't it just be pretty similar? I mean,
I'm just wondering. I'm just thinking. Yeah, I really don't have a kind of argument against. I'm just want to know a little bit more about how the history would have gone. Development of analytic geometry, arithmetization of analysis, and so on. Those would obviously be quite different in the imaginary world, but yet they have no knock-on effect on the come the late 19th, early 20th century, we still get this exactly the same set theory. I mean, in a way, I'm saying maybe you'd be a bit more, even more radical. You know, you wouldn't get ZFC. Why are you assuming ZFC is in there? Is it somehow not connected
I
to
see.
development of analysis?
Oh, maybe we would have some other theory plus DH or something. Is that the idea?
Oh, maybe we had something very different.
Well, you know,
And that's what I don't have an argument that we would.
so when
I'm
you
just wondering why you assume that we don't.
right, yes, okay. I don't know if I have a very good answer, but one observation that you might make is that if you have a robust conception of the hyperreal numbers, and you know that one way of constructing them is with ultrapowers, or if you have, say, a robust conception of the transfer principle, this implies that there are ultrafilters. I mean, you can prove from the transfer principle quite easily. You just take a non-standard integer, and then you say a set is large if its non-standard analog contains that point. So in other words, if it expresses a feature that this non-standard number has. So this was an objection made by who was one of these critics of non-standard analysis that I've written on. I'm sorry, I'm not going to remember the name. But one of the objections that mathematicians might make to non-standard analysis is that it's giving you ultrafilters, which of course is a highly non-constructive thing. And so that suggests that any kind of robust account of hyperreal numbers is going to be connected with non-standard analysis in this way that's giving us ultrafilters and other consequences of the axiom of choice. So those people would tend to look more favorably on the axiom of choice, for example, than otherwise. And so maybe in the thought experiment world, the ultrafilters would play a much bigger role earlier on than they did in actual history, where they were sort of a late construction. I mean, we didn't have the Wash theorem until, the 50s or something like this, right? And so this could have come much earlier if we were better with ultrafilters from an earlier age. Maybe forcing would have been invented earlier, therefore, because it's also connected with ultrafilters in this way. But otherwise, I'm sorry, I don't have a very good answer to your question. Tim.
Yeah, so I'm just wondering how you're understanding what counts as one of these core mathematical theories for which the practice demands that we have categoricity, because I mean, we don't have categoricity for set theory itself, and so presumably you wouldn't count set theory as a core mathematical theory in that sense. Is there some independent way of saying what disqualifies it?
Right. Well, I mean, I think we do have categoricity for set theory in the same style as the Huntington result and the Dedekind result and so on, because we have first of all, we have quasi-categoricity coming from Zermelo.
Yeah, but I mean, that's still a short of categoricity.
Yes, but you can prove a full categorical. In fact, in one of my papers, I do so, but I think the Zermelo only gets quasi-categoricity because he's only talking about subsets of elements in his models instead of subsets of the model itself, which would be full second-order logic. He's not really using second-order logic in his models. He's just the second-order separation axiom that Zermelo needs to prove the categoricity result is saying, take a set that I have, and then I have all the actual subsets of it. But he's not saying I have all the classes that are possible in the universe are subject to replacement. Because if he did that, for example, you might want to say every subset of the universe is a set. I mean, every subset of the universe is a set in the universe. This provides a fully categorical account. I mean, it's not CFC2, it's a strengthening of it, by saying not only are we making sure to have the full width, but also we're having the full height, right? And then you get a fully categorical account. And it's exactly similar to, I mean, it's a set theoretic analog of the categorical accounts of the reals and so on. So I'm not trying to agree, guys, that we don't have a categorical account in set theory. I think we do. The usual way of stating it, you're right, it's just this quasi thing, but there is a way of improving that to get a fully categorical.
But it's kind of then maybe surprising that that isn't a more celebrated result, because this is a requirement of mathematical practice, which is in fact met, but hardly anybody knows that it's met.
Yeah, it's similar to Tony Martin wrote this paper in what is it called? If someone could help me out about the uniqueness of the concept of set. So it's in Topoi, this journal Topoi. So he wrote an article, and the argument given there is basically the categoricity argument that I just described. He doesn't state it that way, but he's talking about the uniqueness of the concept of set. And so you can see in that phrase already that it's something about categoricity. I agree. I think it should be more celebrated. So Robin Solberg and I proved this in our paper on categorical cardinals, which is growing out of his dissertation. I don't know why it's not more celebrated. I don't have any.
Why people don't worry about it.
Somehow, maybe it's connected with this sort of upwardly extensible idea of set theory, that somehow the set theoretic universe is, it's maybe incompatible with reflection ideas, which is part of what Robin and I write about, the tension between reflection and categoricity, right? So reflection says anything that's true in the whole universe is true somehow along the way in a fragment of the universe. But of course, if you think that you should have a categorical account of the universe, then you're going to be denying reflection, right? Because you want your account to be true only for the whole universe and not for any fragment, because that fragment isn't the whole thing. And so there's this tension between these set theoretic ideas of reflection and categoricity that is connected with the reason why we like the quasi-categoricity, and maybe we don't talk so much about the full categoricity. It's necessarily using ideas. The fully categorical account must use concepts to which reflection does not apply, but we want reflection. So maybe that's part of the explanation.
Well, thanks very much, Joel, for a very interesting talk. There's going to be drinks at the Royal Oak, and then dinner at the Giggling Squid afterwards. If anyone would like to join, just come and meet us outside.